A titration is a procedure for determining the concentration of a solution. And so let's say we're starting with an acidic solution. So in here, let's say we have some hydrochloric acid. So we have some HCl, and we know the volume of HCl. Let's say we're starting with 20.0 milliliters of HCl. But we don't know the concentration, right? So question mark here for the concentration of HCl. We can find out that concentration by doing a titration. Next, we need to add a few drops of an acid-base indicator. So to this flask, we're also going to add a few drops of an acid-base indicator. We're going to use phenolphthalein. And phenolphthalein is colorless in acid, but turns pink in the presence of base. And since we have our phenolphthalein in acid, right now we have a clear solution. There's no color to it. Up here, we're going to have our standard solution, right? We're going to have a known concentration of sodium hydroxide. So let's say we have a solution of sodium hydroxide and the concentration is 0.100 molar. And we're ready to start our titration. So we allow the sodium hydroxide to drip into our flask containing our HCl and our indicator. And the acid and the base will react, right? So we get an acid-base neutralization reaction. HCl plus NaOH, right? If we think about the products, this would be OH minus, this would be H plus. H plus and OH minus give us H2O. And our other product, we would have Na plus and Cl minus, which give us NaCl or sodium chloride. So let's say we add a certain volume of base, right? So now this would be higher. And we see our solution turn light pink. Right? So let's say we see our solution turn light pink and it stays light pink. That means that all of the acid has been neutralized by the base, and we have a tiny amount of excess base present, and that's causing the acid-base indicator to remain pink. So a tiny excess of base means we've neutralized all of the acid present. And where the indicator changes color, this is called the end point of a titration. Right, so when our solution changes color, that's the end point of our titration. And here we stop and we check and see the volume of base that we used in our titration. So if we started right here, right, if we started with that much base, let's say we ended down here, right? So we still have a little bit of base left, and this would be the volume of base that we used in the titration. Right, so we have a change in volume here. And let's say that it's 48.6 milliliters. So it took 48.6 milliliters of our base to completely neutralize the acid that we had present. And so we can now calculate the concentration of the HCl. All right, so let's go ahead and do that. And let's start with the concentration of sodium hydroxide. All right, we know that we started with 0.100 molar solution of sodium hydroxide, so 0.100 molar. And molarity is equal to moles over liters, right? So this is equal to moles over liters. And our goal is to figure out how many moles of base that we used to neutralize the acid that was present. Right, so we can take our volume here, 48.6 milliliters, and we can convert that into liters. Right, so just move your decimal place 3 places to the left. So 1, 2, 3. So that's 0.0486 liters. So this is equal to moles over 0.0486 liters. And so let's get some more space. All right, let me just rewrite this really quickly. 0.100 is equal to x over 0.0486. So we're just solving for x, and x represents the moles of sodium hydroxide that were necessary to neutralize the acid that we had present. All right, so when you solve for x, you get 0.00486 moles of sodium hydroxide used in our titration. Next, you look at the balanced equation for what happened, right? So if I look at my balanced equation, right, there's a 1 here, right, and there's a 1 here. So we have a 1-to-1 mole ratio. And the equivalence point is where just enough of your standard solution has been added to completely react with the solution that's being titrated. And at the equivalence point, all of the acid has been neutralized, right? So it's completely reacted. And since we have a 1-to-1 mole ratio, right, if I use this many moles of sodium hydroxide, that must be how many moles of HCl that we had present in our original solution. So therefore, I can go ahead and write that I must have had 0.00486 moles of HCl present in the flask before we started our titration, right? And I knew that because of the 1-to-1 mole ratio. All right, remember our goal was to find the concentration of HCl, right? The original concentration. And concentration, molarity, is equal to moles over liters. So now I know how many moles of HCl I had, and my original volume of HCl was 20 milliliters, right? So right up here we had 20 milliliters. So I need to convert that into liters. So I move my decimal place 1, 2, 3. So I get 0.02 liters. So now our final step here to calculate the concentration of HCl, right? So the concentration of HCl is equal to how many moles of HCl we have, which is 0.00486 moles over liters of solution. And we had 20 milliliters, which is equal to 0.0200 liters. All right, so now we can take out our calculator and do this calculation to find the concentration of HCl that we started with, 0.00486, right? And we're going to divide that by 0.0200. And we get 0.243 for our answer. So the concentration of HCl, right, is equal to 0.243 molar. So we've solved for the original concentration of HCl. There's a shortcut way to do this problem, right? And the shortcut way would be to do the molarity times the volume of the acid is equal to the molarity times the volume of the base used. So MV is equal to MV. So let's say we have the acid over here on the left and the base over here on the right. So the molarity of the acid is what we were trying to find. So I'll just make that X. The volume of the acid that we started with, you can just leave this in milliliters if you want. 20.0 milliliters is how much of the acid we started with. And for the base, we knew the concentration of the base that we used in our titration, right? It was 0.100 molar. And we also knew the volume of base that we used to completely neutralize the acid. We used 48.6 milliliters. And notice how the mLs would cancel out here, right? And we can just go ahead and do the math and solve for x. So we get out the calculator, and we need to multiply 48.6 times 0.100, right? And so we get 4.86, obviously, and then if we divide by 20, we will get our answer of 0.243. So x is equal to 0.243 molar. And this shortcut way works pretty well when you're dealing with a strong acid and a strong base in a 1-to-1 molar relationship. All right, in the next video, we'll do a problem where the mole ratio is no longer 1-to-1.